Hello, and welcome to this session. My name is Lloyd Gom. I'm Vice President, Business Development and Marketing for Delta Q, one of the ZAPI group of companies. As I said, I'd like to welcome you to this session. This is called Moving a New Machine to Electric Drive at a System Level. With me, I've got a very experienced panel, and I'll introduce you shortly. Just a couple of housekeeping items. If during this discussion, if you have a question, note that you can add it to the Q&A on the top right. I'll see your question and then I'll be able to anonymously feed it to the panelists. Also note that this session is recorded and you'll be able to listen to it at the end of the conference. So to get started, as I said, we're going to be discussing moving a new machine to electric drive. So what we were envisioning here was a new piece of equipment. Maybe it's got an internal combustion design already, and we're going to discuss this like an original equipment manufacturer trying to outfit with electric drive. So to get started, I'd like to introduce you to each of our panelists. With us is Mirko Baggio. He's our Business Development Director for ZAPI Group. He's based in Sweden, and he's been with ZAPI for 16 years. Also, we have on the panel Benny Forsman. He is our Business Development Manager for Inmotion, a ZAPI Group company. He's based in Virginia and has been with ZAPI for over 2 decades. And Gareth Jones, he's our Managing Director of ZAPI UK. He's been with us for 17 years at ZAPI. And also joining us from outside ZAPI is Paulo, and he's the Managing Director for 4M Consulting. 4M Consulting is a partner of ZAPI. We do a lot of work with Paulo and his company. He's got a doctorate in high voltage power electronics and adds specific expertise in system design, software, and system. And he's based in northern Italy. So welcome, everybody. To get started, Gareth, why don't we start the conversation on the sizing of different components? This is a place where a lot of customers, as we know, start. So maybe you can sort of contextualize how to size batteries, motors, DC to DC, converters, inverters, chargers, sort of all the elements at a high level.
Sure. So hello, everybody. So the sizing of the components is obviously an important thing and an important first step. So many OEMs now are looking to develop new electric vehicles and to convert IC-powered vehicles to electric. The momentum pushing many industries in this direction is growing, and today we're going to talk about some general and generic themes which cross over into many applications. So as Lloyd said, I will run through some of the key components and highlight some considerations that are useful for an electrification project. So first of all, the battery. The battery is the most critical part, as it is the most expensive, the most difficult part to package, and it's critical for the operational duty of the vehicle. Often at the start of an evaluation into an electric vehicle, the biggest question mark is about the duty cycle. How much energy is needed to allow the vehicle to operate for an acceptable working shift with an acceptable or typical duty cycle? So firstly, the difficult question to answer is what is an acceptable working period and what is an acceptable duty cycle? Rarely are these questions easy to answer. So especially if the vehicle has previously been running with an IC engine where due to the use of diesel fuel, the level of detail around the energy consumption has not really been required. So often the starting point is a worst case scenario duty cycle and working day, which may point the designers towards a battery which is too expensive or physically too big to fit into the machine. With cost and space, 2 quantities usually at a premium, some deeper evaluation is required to understand if a battery-powered machine really can do the job. Some OEMs have telematics data from their machines, which is really valuable, as this can give the designers more confidence to allow them to downgrade from this worst case scenario, which is normally a scary worst case scenario about the kind of energy they need. But also, without any reliable telematics data, we typically would make some calculations using the vehicle and application specifications. So we'll take the weight, the speed, the max grade, and things like this, and we would make a matrix of the different working points. So perhaps we will consider driving fully loaded on the flat as one function, driving without load on the flat as another, and other typical driving conditions for that specific application. Also, most projects, there are other functions we need to take into consideration, for example, hydraulic lifting or steering. So we'll make a list of all of the functions, and then we will calculate the energy usage of each of the functions at the reference working points. And we'll work together with the OEM to make some duty type estimations. So we know the energy needed for the function, the time of the function, and the frequency of each function. So we can plug this data into a matrix, and this will allow us to see how much battery energy is needed for different scenarios. Usually everyone overestimates everything, and because everyone is scared of under specifying the battery because of range anxiety, but at least you start to get a reference of the ballpark you are looking at. And the outcome of this evaluation about the energy usage will questions and decisions. For example, do you need a range extender option? Or what battery technology do you need in order to fit the required kilowatt hours into the physical space that you have available? And also, unfortunately, often you might need to consider if you need to adjust the performance specification. Maybe the performance specification you were shooting for doesn't work because of the amount of energy that you need. So perhaps you can downgrade the performance specification. And another important thing is, will the end user pay for the machine when you consider the cost of the specific battery that you've decided upon? So you can see that getting an accurate picture of the energy requirements is critical at the start of the project. But even with all the calculations, modeling, estimations, nothing beats results from real testing. So making a concept machine will always shine a light on the real requirements. I was going to ask Benny from Inmotion if he can explain how the functionality inside the ACS motor controller can be helpful for OEMs in order to get this data.
Yeah, I can jump in. I mean, I will first of all support what you were saying, Gareth, that it's really different from machine to machine. I mean, we have customers where the sizing is kind of easy because the requirements are really known. I must have this maximum speed. I must be able to climb a particular ramp. Let's say a scissor lift. It must get up the ramps to get up on a flatbed trailer. If it can't do that, you can't move it. So these things are easy to do. We have calculation tools that do what you say. You look at the gear ratio, the speed, and all of this. But more commonly is where the OEM won't really know. And we say, well, we're using a 40 horsepower diesel today, so we think that we need a 40 horsepower electric machine. And as Gareth also was saying, in most cases, this is oversizing and over-specifying things to a level that makes it not really cost effective. You do have some applications where, yes, this is the case. The machine is using a 40 horsepower engine and it's using full power at full speed at all times. And then, yes, okay, that's the duty cycle that we need to hit. But more commonly, the 40 horsepower engine was selected to create a dynamic behavior that is acceptable to the user. and you're using it at different speeds and different loads. So one of the most common things that we do, okay, you build a concept machine, and in our case, we use the built-in logging, just looking at when the prototype machines are being used, what is the operator really doing? How much time has this machine spent at this speed, at this torque, during the duty cycle? And with that kind of data, now you can really start sizing the system a bit more effectively, saying, well, you can actually, maybe you can cut out these outlier positions because it wasn't really important for you. And you find the space that the machine is used for 99.9% of the time.
Yeah, there's no substitute for that real data that you can get from the testing.
And I'll jump in and say another thing that is quite helpful is also today we can program a simulated speed torque curve in the controller. So even if you're using a larger controller for your concept machine build, by programming a different speed torque curve, you can easily simulate this is the performance you will get if you use the smaller motors. And this is the performance you will get if you use a smaller controller, and let the OEM have different operators to run the machine and test the performance and give feedback.
Well, actually, I think, Benny, that you exactly target the point, which is the trade-off between the packaging constraint in the machines and the performances expectation. Because and this is actually also our experience, if you prepare the more accurate simulation, then you can not easily, but you can predict with some confidence which is the final performances. In my experience, this is just the first step, because actually then the second step is to convert this simulation into the software control for the hybrid control unit, no, or whatever it is, fully electrified or with the range extended with the combustion engine, actually. So I personally, I totally agree with you, and this is also our experience. We started also from the duty cycle, but this is the very first roadblock. Maybe we are so unlucky, but most of our customer or potential customer does not know which is the power absorption of their machines, of their system, even if they are building and producing these machines since decades, no? But when you ask a duty cycle, sometimes they handwrite some notes on a paper, and then that's why we are normally making a first step, asking and providing the field campaign, the field testing campaign before the electrification, in order to really measure which is the duty cycle, and not to just believe on what is their idea sometimes, no?
I can jump in and add a comment. I think there is an important distinguish to do, because today the most of the applications are using internal combustion engines, and the power that these engines can provide, the peak and the continuous power, are almost the same. For electric motors, it's totally different, this ratio. You can have twice maybe even more, the peak power of an electric motor respect to the continuous power. So it's important to know very much the duty cycle in order to make the right sizing of components. And is the reason why, if you have today an AC solution where you have a 50 kilowatts engine, you convert in electric, probably you have to install 30 kilowatt electric motor. And this is the main reason, because there is differences in peak and continuous power that the electric motor can provide.
I was going to ask Paolo about applications that you're working on and focusing on the battery side of things. I guess physically packaging the battery into the machine is always a big challenge. When we think back to forklift truck applications, which many of us here are very, very familiar with, the machine was almost designed around this big battery. But now on a lot of the projects where machines are being converted, it's a case of where can we fit some batteries. So I guess that's quite a challenge for some of the projects you will be working on, packaging of the batteries.
Was that Paula, did you have a comment on that? I think that's what Gareth was suggesting, if you had a comment on the packaging of batteries and sort of the time frame that you have to spend helping customers with that.
Yeah, that's the reason why since we start from the design of the electrified powertrain integration, and actually we never found a battery solution that can fit all across the different platforms that we have had. And this is the reason why now in a very not very much, but we are producing customized battery, because actually the difficulty was to find the exact matching between the battery performances and the packaging. I remember that we started, and Mirko probably remember as well, the first hybrid tractor that we made together for Carraro, and the program constraint was that the tractor, because it was a vineyard tractor, so very compact, very small, we customized what I frankly, I called it a crazy battery, because it was impossible to package any standard box, and then we adapt in a very crazy way the batteries to the vehicle. So this is frankly, I think that Gareth identified the focus. It's difficult to match every component, but the battery is really the core of this solution.
Yeah, thanks.
So what we discussed so far, we just started with sizing. So, and what we've heard so far is for customers, for advice, that they need to do basically an energy study and understand duty cycle, how much energy is flowing through the system, what the equivalent equipment might be, and also what some of the cost trade-offs would be, because you don't want to over-specify. So we've chatted about that, as well as some battery packaging. I guess one question I have for the panel is, how long does that process typically take? I know there's not a one-size-fits-all answer, but you know, you guys have collectively got like over 60 years experience working with customers to do this. You know, what sort of guidance would you give the audience on how much time to sort of budget for this exercise to get it right?
Of course, yeah, it depends massively from one application and one customer to another, but always longer than you think, I would say, is the quick answer. But And it depends on what level of information you're starting out with. If you have some good telematics data from the vehicle, that helps. Or if you have to do all of the testing and evaluation from scratch, then that will take longer. But we see a range of from several months to a couple of years to get everything through this process.
Right. And starting with design, understanding the energy, and then eventually logging an actual performance with the machine in situ. So that's good. I guess the other sort of key thing, and maybe we can start talking about, a topic that, typically people start with the battery they want to use. And selecting the right system voltage obviously plays a big role. Benny was talking about this yesterday a little bit, and how we've all been trained as consumers from the tool industry to kind of think, oh, higher voltage is better. Anyway, maybe chat about that, the trade-offs between selecting different system voltage. Did you want to start, Mirko?
Yeah, that's fine. So, yeah, of course, to answer this question, what is the right voltage level for my application is not easy. Depend very much on the power that you need. I can start, let's say, with a statement, if you like. And based on our experience, all the OEMs, they tend to stay as much as possible below 60 volt of the battery. Why? Because they can avoid to have complication in the system. This voltage level is considered safe. And I hope you had the chance to have a look on the very interesting presentation made by Murad on the first day, where he presented very much this topic, explaining why all the people want to stay below 60 volt. But of course, this is in order to have a very simple layout and system. Then, of course, if you stay below this voltage, the power that you can handle is more or less limited. We can consider maybe to reach 20, 25 kilowatt continuous maximum as power. So it's valid for compact machine. But if you need to go above this power, you need to select a higher voltage, of course. And how much higher? Can we stay 96, 120, or do we need to go above? And so also here, there are some other considerations to do. If you stay below, let's say, 150 volt, in terms of components, you can have a wider range of products that are more or less coming from other markets or existing markets, like, for example, forklift. And still the complication or the training you need to offer to your operators, to your service team is rather limited respect if you go above to 350 or 700 volt or other voltage range. But of course, again, if we are talking about very high power vehicles like 200 kilowatt power, there is no way to stay below, let's say, 650, 700 volt. Yeah, maybe just to give you shortly an idea, maybe Paolo wants to add some comment.
Yeah, actually, I totally agree with you, Mirko. The first hurdle is the cultural is a cultural trend, because actually, people are basically scared to step up to high voltage from low voltage, from 48 or 96, because there is the long history with forklift, which is the pioneer of the electrification, basically, no? and so people are scared to move up. Also in our experience, and we have produced many different batteries for many different powertrains. That as higher is the power, as higher is the voltage. Of course, normally, roughly, we can identify a threshold over 100 kilowatt is I would say mandatory to use voltage over 400 or better 700. Also because there is the very important fallout of components from the automotive. So normally, if the customer that wants to electrify a machine thinks that it's easier to have a low voltage, but the problem is that, of course, the current are so high, and therefore you have to increase significantly the cost. On the other hand, if you use a high voltage battery, and it means lower currents, you can use thousands of components that are in production for automotive. So are standard, are I would say already well integrated, because all these components are normally communicating via CAN, so are not just hardwired or with poor communication protocols, no? And then I strongly believe that especially for the larger non-road machinery, or even the last very interesting area, which is the marine and the nautical vessels, are very power demanding, and therefore the high voltage is the mandatory path.
Yeah, it makes sense.
But I'll jump in to say that I really think that this is driven. It is and should be driven by the power requirements, because I would say I fairly often see requests for, let's say, a 20 kilowatt system, but we want to run it at 650 volts, and you sort of say, well, I hear you, but it's not really an ideal sizing of your system. It will make for a big battery just to get to the 650 volt, and you are going to use fairly oversized components for this power need. And even on the auxiliary side, I would expect much more seeing sort of distributed voltages in the vehicle, where you may have a 650 volt for your traction axis on a big machine, but you run your low power auxiliaries on a 24 or a 48 volt bus, because it simplifies the distribution throughout the vehicle and makes it long term a whole lot easier to service and maintain.
When we started, one of the trade-off discussions on system voltage was, real and perceived safety, so the sort of touch safe voltage, but moving up in power, given the size of the conductors involved and other components, we're forced to go up in voltage, essentially. Although the voltage you select also has consequences and trade-offs on the other components you select. I guess just where do you guys think this is going, say, for the construction industry? We know that's a big market that is starting to tip to electric. What sort of system voltages are you seeing there? I know it's dependent on power, but maybe you could simplify it for everybody and kind of give us a range from compactor type products to wheel loaders and sort of everything in between.
Maybe I'll just jump in while I still have the chance then. So I think what we see 48 volt, and as mentioned, up to somewhere 20-25 kilowatt of continuous duty. When you go above that range, we see a lot of 96 volts right now. And when you go above 40 kilowatts of continuous power, that's when you cross that you cross that bridge into the really high voltage areas, and there I think we see mostly 650.
I definitely see a trend that companies prefer to start with the low voltage, where there's a lot of crossover from, for example, the material handling market, so they can focus on their small range machines on low voltage and use low voltage equipment, 48 volt, for example. But then, of course, the same situation as with all sectors. As the machines get bigger, eventually the voltage needs to get bigger to maintain sensible amounts of current.
I've got a question for the panel, actually specifically for Paolo. The question is from Roberto. Which is for you the voltage gate between batteries to save money? I don't know if I said that right. I think the question is, in your mind, what is the best system voltage to save money on the battery investment, or is there one?
Hard question and a hard answer. I think that, of course, as Benny was saying, if the power is in the range of 20 to 40 kilowatt, there is no reason to increase the voltage. But the economical trade-off, I think that is in our experience over to 350 volt. If 350, 400 volt is the correct sizing for the electrical system, then over this normally the components and also the design of the battery allows us to reduce the cost for many savings that are possible, not only, as I said, due to the component which are normally derived from the automotive market, but also for the packaging and for many. Actually, we are experienced with the lithium iron phosphate chemistry. We have very little experience with some other, but normally for the machines and for the boat and for this chemistry since years. And again, I think that roughly the trade-off could be economical wise acceptable in the range of 400 volt.
Yeah, I guess it's driven by availability of the components for each voltage. So if you can use 48 volt, for example, you have a huge availability of components from the material handling. If that's not big, then you look at 350 because you have a huge availability of components and a growing availability of components from the automotive. And then the next step up for us would be 750 volts in that area because of the availability of components for the bus and truck market. A couple of great points where you can.
Although I have heard anecdotally from some customers that getting the attention, an industrial OE getting the attention of an automotive supplier is sometimes difficult given the different levels of volume we're talking about.
Yeah.
That's a story for another day. Gentlemen, I got some questions around motor technology. Maybe we can shift a little bit to that. We've talked about, again, energy requirements, characterizing the machine. We've talked about a little bit about battery packaging and system voltage and the trade-offs there. What about motors? What would you like OEs who are thoughtful on this discussion to be thinking about on the motor side?
Yeah, I can say something. Anyway, before to talk about that, I will encourage our attendees to have a look on a couple of presentations made by our colleagues, Mr. Kruse, that I found very interesting. He did one today and one yesterday regarding specifically motor technologies. But I will maybe try to give you some suggestions. I stolen to him a couple of slides. Let me check if I can find and project something. I hope you can see.
Sorry to interrupt. While you're looking for that, and we had a question from the audience as well. While you're answering, could you also think about what sort of the cost implications of choosing different system voltages might be on the controller and motor side? Not specific, but sort of trend, things that people need to think about high level.
So there's more cost related to the high voltage equipment from the point of view of safety and the cabling. So you have to consider the increased costs around the safety aspects of the system. Point.
I'll give two rules of thumb that are not always correct, but we kind of used to say that when it comes to the motors, size and cost depend on torque. And when it comes to the inverters, size and cost depend on power. And if you are looking specifically within close range, it means that the voltage doesn't really have that much impact on the cost. But then, as Gareth says, making the step into the high voltage space where you need the custom cabling and the HVIL systems and things like that, that makes a relatively significant cost difference compared to staying below 120 volt, even more so below the 60 volt.
Okay. Marco, we can see your slide.
Yeah, okay. So as I said, I've stolen a couple of slides from Mr. Kruse. So here you can see comparison on different technologies, motor technologies that are widely used in mobile applications. And of course, all of them has advantages and disadvantages. So in the left, we see motors without magnets inside. Here in the middle, we have motors with low-cost magnets. And here on the right, we have motors where the cost of the magnets are important, these rare earth magnets. And
I think I looked at the wrong slide, Mirko. Sorry, I think I'm looking at slide number 2. That's okay.
Is that okay now?
Yeah.
Okay. So three families basically of no magnets, low cost magnets, and high cost magnets, and all of them, of course, has different performances in terms of peak efficiency, in terms of torque density, constant power range, and general material cost. So all of them, as I repeat, has different characteristics. So, and all of them are used today in a mobile application. So the importance when you need to define a specific application, a specific function to be electrified in your vehicle, is important to understand what is the best of these technologies to be selected, and based on these kind of performances. So, for example, if you need a very compact machine, I will suggest probably to stay on the right side where you have very strong magnet inside and can deliver a lot of performances. But of course, you need to be prepared to pay more. If you need, let's say, good efficiency, but you want to have also a look on the cost, probably you need to stay in between. And if the efficiency is not your first target, but you want to stay more on the low side of the cost, you stay on the left. In the next slide, we have tried to analyze or to compare a little bit the two solutions here in the middle, because these two are today the most, I don't want to say used, but the most promising or the most important technology where we see probably the future of mobile applications. So here in the left, you see what we have called SRPM motor. And this kind of motor has a torque curve made like you see in the screen, where we have a small constant torque range with a very high torque and a very wide constant power region where the torque is going down following this curve.
I can't see this. Okay, I think I'm still looking at the previous slide. So yeah, that's it. Thanks.
Okay, so I will try in this way. So the constant power region you can see on the right is wider and is typically used, this kind of torque profile, in traction applications where you need a lot of torque to maybe climb a steep ramp, but also you need to go fast in speed, high speed, with limited torque when you go on the public road. So the technology here recommended is SRPM for this kind of applications. Other case is the IPM solution, spoke IPM, here on the right, where the constant torque region is much wider. So you can see here we have much wider range. Even the peak, so the value of the torque is typically limited, and the constant power region is smaller. So this kind of motor is more suitable for constant speed applications, like, for example, hydraulic pump, or I also indicated here on purpose the traction for AGV applications, where AGV, they have a special demand for traction that is not the typical vehicle going on the public road. So just to explain that also for these two technologies, there are case by case, we need to identify the right solution, the right compromise for your application. So quickly, I go to the last slide. Here is an example where we have make a comparison between different motor technology, so SRPM and spoke IPM, with the same mechanical dimension and same peak current. So you can see that the peak torque available is much higher in SRPM motor respect to the spoke IPM motor, but in the other way, the region of constant power, that is where the curve is going down, basically, is much wider in the SRPM respect to the other technology. So this basically is showing and is explaining, as I said, that we need to evaluate carefully before to select motor technology to match correctly the applications that you need.
That makes sense. There's obviously trade-offs. So it's thank you, Murad, thank you, Mirko, for showing that. Could you generalize in the business what are we seeing a trend toward specific motor technology, or is it a blend? In terms of what people are actually selecting in their designs.
I think
Well,
you can say blend for sure, but of course there's a trend for an increased amount of permanent magnet motors in most industries because the efficiency are becoming more and more important, and the designs are becoming better as time goes on. So we're seeing a trend towards the more efficient motors in general, but of course there'll always be a mix.
Okay. Just to point out, we're running low on time. We've got about 6 minutes left. We do have a question from the audience related to motors and controllers. Do you have any thoughts on centralized versus distributed systems? Example, a single motor versus 4 to 6 motors for specific cost and performance goals.
So perhaps on a hydraulic system, you could have distributed hydraulic motors around the machine, or you could have one big electro-hydraulic motor to drive the system. And again, you have to look at each of these case by case because there'll never be one correct answer for all different machines. But in general, the more components you've got, the more separate motors you have on the machine, the more complex the machine will tend to be. But there could be other driving constraints regarding where to package these parts. And perhaps another benefit to having separate motors distributed around the machine is you could maybe get away with using a lower systems voltage because instead of having one 100 kilowatt motor, you can have 5 20 kilowatt motors, which could justify using a lower voltage if that was preferred by the customer.
But would you say a distributed system in general would be a higher cost? Is that a generalization you can make?
I would say so.
Okay, so there's a definite performance cost trade-off there.
Yeah.
The last section we were going to talk about was what advice can the panel give to OEs looking to properly integrate selected systems with existing systems? Who can sort of take that on just to kind of give a quick outline before we close?
May I start?
Sure.
Okay, good. Well, actually, this is the I think the other key of the correct integration, because normally all the machines need to have an evolution and not a revolution, because for many reasons there is the service which is already in place and trained to troubleshoot the machine with dedicated tool which are existing, and so you cannot simply because of the electrification of the machine, for example, you cannot simply change completely the system, and so you have to in some way to convert the service tools in order to also to make the troubleshooting for the electrified machine. But this is just an example. Normally, my feeling is that the way to well integrate the new system with the existing is to prepare and establish a very good communication between the for example, the HMI, which does exist, and which exist in the machine, and the new components that are powering the system. So I think that the first point is the communication protocol. So to prepare a good software that can handle all the existing functions, because remember that normally when a new machine, a new electrified machine is created, normally at least the new machine must have the same performances of, for example, of the diesel one, of the current diesel one. And so performances not only in terms of power and of course functionality, but also in terms of interaction between the machine and the operator. So I think that this is the focus has to be on the software and on the I would say on the algorithm that are the base for the functional system.
Thank you. I think we need to wrap up. We're getting short on time for some folks on this panel to move on to other presentations. So I'm going to do a wrap up. Thank you, gentlemen, for your time. I think we covered a lot of ground and at least provided some overview advice on how to approach these questions. Again, the topic being moving a machine from to electric drive from another energy source. So I think we've provided the audience with at least some of the things on the scoping side and what we recommend as first steps. Obviously, not all cases are the same. So these are generalizations. For the audience, if you do have additional questions that you'd like to field, I might suggest going to the networking session on the event platform and posting a question there, and we'll get back to you. Otherwise, thank you for your time, and realize that ZAPI Group of Companies, we do have a lot of expertise and a lot of years of experience on guiding customers through this journey that we just spoke about. So Mirko and Benny, Gareth and Paulo, thank you very much for your time. And with that, we will close.